So now we will study the case where we want to construct a graph which is beyond a tree structure. So in the first part we considered how to construct graphs that had a tree structure associated with them. Now we will take the next step and consider graphs that are beyond tree structures. So suppose we of each data vector that we have consists of d features. And let's say for simplicity they are in the Euclidean space, so each xi is a real number. And as before, we'll assume that xi's are the features of the observed vector. Now our task is to generate a graph G which is of the form V comma E, where V is the set V1, V2 up to Vd, which are the vertices of G, and E is the edges. In particular, E, we'll use the notation E of jk is 1 if there exists an edge between vertex j and k, and ejk is 0 if there is no such vertex. Okay? The first type of graphs, in fact the graphs that we will study in today's lecture are correlation based graphs. Marginal correlation. These are the only types of graphs. Later on we'll study other types of graphs that capture conditional independence and so on, but we'll start with the case of marginal correlation graphs. So here we let rho jk be some measure of correlation between vertices, say j. I will use the notation vj, vk or j and k interchangeably, it means the same thing. So if there is some correlation between vertices j and k, then rho jk is a function that captures it. I'll also use the notation rho of xj, xk to mean the same thing. This means that the correlation is calculated with respect to the random variables xj and xk associated with the vertices j and k. So all these notations are equivalent and don't get confused. In marginal correlation, we put an edge between the vertices between j and k, that is E of jk is plus 1 if rho jk is significant, meaning it is greater than some epsilon, where epsilon is strictly greater than 0. Okay? So the measure rho jk must satisfy the following. We say that the random variable x is independent to y, then if x and y are independent, then rho xy should be 0. So the correlation must satisfy that if x and y are independent, rho xy should be 0. If we say rho is a strong correlation if the opposite is true. If rho xy is 0, if and only if x is independent to y. So not all correlation measures that we will discuss will be strong. In fact, most common ones are not strong. But there are a few ones that are strong that you should know about, so we'll discuss that. In addition, for practical purposes, we need that rho of xy must be easy to compute. It must be robust to outliers, etc. So the first correlation measure that we will compute is the Fearsome correlation. So what is this? Rho of xy is defined as the covariance so the first measure that we will study is Fearsome correlation. It says that rho xy is the covariance between xy divided by sigma x, sigma y. So sigma x and sigma y are the square roots of the variances or the standard deviation of x and so on. Now, this assumes that we know the statistics of x and y. It's very easy to produce sample estimates if you are given some data points. So if you have, say, feature x, feature y, and you look at your samples, in the first sample, the feature of the first sample at x is x1, here it's y1, here it's x2, y2, up to xn and yn. Then we can define the sample correlation between x and y is defined as follows. First, we define the sample means. X bar, which is 1 over n summation of xi, y bar, which is summation of yi, then the sample errors. Sample errors are defined as Sx, which is square root of 1 over n summation of I going from 1 to n, xi minus x bar square. This is square root of 1 over n summation of I going from 1 to n, yi minus y bar square. And then the sample correlation, which is what we are interested in, is computed as gamma of xy, which is the summation of I going from 1 to n, xi minus x bar, yi minus y bar, divided by sxxy. So this is how we define the sample correlation. The way we use it is we are given a feature x, which is x1 to xd, uh, the correlation between xj and xk will be denoted by rjk, or actually rho jk, and we let rjk be the sample estimate of rho jk. So now we have some graph consisting of d vertices, and we want to decide whether we should put an edge between xj and xk. Okay, so the way we will decide this, whether to put an edge or not, is that we compute the sample correlation rjk, and we want to make a decision based on this. So we have to really make a decision, consider this as a hypothesis testing problem. Where we have two hypotheses, H0 and H1. H0 considers the case where the correlation, the true correlation is 0, and H1 considers is the case where rho jk is actually non-zero. It can be positive or negative. And so we want to distinguish between these two hypotheses. And the most common approach for doing this is thresholding, meaning that if the magnitude of our sample correlation, let me just use the notation rho jk, so I'm consistent. So if the sample correlation is greater than alpha, then we have sufficient evidence to reject H naught. That is, we reject the fact that the correlation is 0 and put an edge between the vertices j and k. This is not the only approach. This is the simplest approach, but we can have some slightly more complicated methods, but they give us more precise guarantees. So a more sophisticated test is to use permutation testing. So what we do here is we look at the two features. So feature xj, feature xk. Let's say we have n samples. This will give us xj1, xj2, xjn. These are the observations in the n samples for the jth feature. These are the observations for the kth feature. What we do is we randomly permute to one of the columns. And we estimate the correlation after permutation. And let's say our estimates are rjk of 1, rjk of 2, up to rjk of n, or rjk of p. So we permute this column to a total of b times. And what we do is we define the quantity p to be 1 over b times, we look at the fraction of times our sample correlation in this random permutation has exceeded the original quantity that we estimated. And if P is sufficiently small, then we know that RJK is large and we can reject the hypothesis H0. So P here has a name to it. It's known as the P value of our estimate RJK. And the point is that if P is sufficiently small, we can reject H0 and put an H between J and K. Now there are other methods. We can also compute confidence intervals. For RJK, perhaps the most popular method is the Bootstrap method. And to show how to construct the confidence interval, we define the following function. This is very similar to what we did when we considered the study of training error and test error, E in and E out. So we define Fn of W to be the probability that square root of n times the max over St RST minus rho of St. This is the true correlation. This is our sample correlation. N is the number of samples. This is greater than W. If we set Fn of W to be alpha, then W of alpha is defined as Fn inverse of alpha. And then the confidence interval, this is the same calculations we had done before when we discussed the relationship between the training error and test error in pack learning. This is RST minus W alpha over root n to RST plus W alpha over root n. This is the confidence interval that we get. So if we know the function Fn of W, we can get the confidence interval like this. Now the question is, we do not know Fn of W in practice, and we estimate it using what is called the Bootstrap method. So in bootstrapping, what is done is that we are given our data set D, which is x1, x2 up to xn, and we use it to generate total of B sample data sets by sampling via replacement. So D1 will be the data set y1, y2, or actually let me write it like this, y1, y1 of n, where each yi y1 of j, or let me finish it. So this is the first data set we have. D2 is y1 of 2, y2 of 2 up to yn of 2, and db is y1 of b, y2 of b up to yn of b. And the idea is each yj of k is sampled uniformly from x1, x2 up to xn. So independently of all other samples. So now we have b copies of the data set D. For each dj, we will estimate the sample correlation RST of j for all s and t, and delta j will be defined to be square root of n times max of st of RST of j minus, so RST is the sample correlation between features S and T for the true data set D. This is for the jth bootstrap version. And then what we do is we estimate f hat n of w to be just the empirical fraction of times the bootstrap version is greater than w. And this is the estimate of fn of w. Once we have it, we can then use that to compute the confidence interval. C hat st to be rst minus w hat alpha by root n and rst plus w hat alpha by root n. And there is a theorem which says that if d is not too big, which means it is at least less than e to the n raised to 1 over 6, but so it's still sufficiently large, it can be larger than any polynomial function of n, then with probability greater than 1 minus alpha, rho st will lie in the interval CST. So if you really want to be rigorous, you can use this sort of method to compute the confidence intervals. However, in practice, often a permutation test is sufficiently good, or you can just use a simple thresholding based method. So all these methods can be used in practice. Now, I will talk about other correlation. All of this was when you are using the Pearson correlation function, but that's only one of the methods. Another method that is widely used is Kendall's tau. So the main issue is that Pearson correlation is often not robust to outliers in the data set. So an alternative correlation measure is the Kendall's tau correlation, which is defined as the expected value of sine of x1 minus x2 times y1 minus y2. So you take the product of x1 minus x2 and y1 minus y2 and take the sine of it and take the expectation. So here x1 and x2 are sampled IID from the distribution Px, y1 and y2 are sampled IID, or actually I should write it more properly. Here x1, y1 is sampled from the joint distribution P of xy, and x2, y2 is independently sampled from the joint distribution P of xy. And so these are independent samples. In other words, if we consider two features, And we consider two samples. Feature 1 will have x1, y1, feature 2 will have x2, y2, and we can use that to estimate the Kendall-Stowe correlation. It can also be interpreted. There is a geometric interpretation for this, which I will do it on the next page. Imagine that you have the two data sets. So this is the x-axis, this is the y-axis, this is the point x1, y1, and this is the point x2, y2. So here x1 is greater than x2 and y1 is greater than y2. So if you look at the sign of this quantity, then this is going to be positive. So this is known as the concordant pair. If you had points like this, so this is x1, y1, x2, y2. Then here x1 is less than x2, but y1 is greater than y2. So the sign of x1 minus x2, y1 minus y2 is negative. This is known as the discordant pair. So we can interpret tau of xy as the probability that you get the concordant pair minus the probability that you get the discordant pair. We can do a sample estimate if we have just data points. You take all n choose 2 combinations of s is not equal to t, sine of xs minus xt, ys minus yt. And we can use the permutation test to compute the p-values for statistical significance as before. Now, however, just like Pearson correlation, Kendall-Stowe test is not strong. So that is rho of xy equals 0 will not imply that x is independent of y. We can just say the variables are uncorrelated. They are not independent. So the next two tests that we will study, it has the main property that if rho of xy is 0, then x and y are actually independent of each other. And so we'll study two tests of this form: the distance correlation and the last one is tau star correlation. So the next measure of correlation is distance correlation. To define it, we actually require 4 independent samples. Then we define gamma square of xy to be 1/4 of the expected value of b of x1, x2, x3, x4, and b of y1, y2, y3, y4, where b of z1 to z4, so it's a function of 4 variables, is the distance between or difference between z1 and z2 plus z3 and z4 minus these quantities, z1 minus z3 minus z2 minus z4. So now the distance correlation function is defined as gamma square of xy divided by the square root of gamma square of xx and gamma square of yy. It satisfies the strong correlation property, meaning that it can be shown that rho of xy is between 0 and 1, and rho of xy is 0 if and only if x and y are independent. However, in practice, there is a problem with this measure, which is the same as in the standard Pearson correlation, in that it is sensitive to outliers. Also, it is hard to get confidence intervals for this measure. So the next measure of correlation, and the last one we'll discuss today, is tau star correlation. It's also defined using 4 copies of random variables. Where x1, y1 to x4, y4 are IID copies of pxy, and a of z1 to z4 is now the sign of z1 minus z2 plus sign of z3 minus z4 minus the z1 minus, or the absolute value of z1 minus z2 plus the absolute value of z3 minus z4 minus the absolute value of z1 minus z3 minus the absolute value of z2 minus z4. So this is the same as the distance correlation definition, but we put a sign in front of this. Tau star can be approximated using the empirical estimate given a data set like this. So we take all 4 tuples, all distinct 4 tuples, and choose 4 of them and take the empirical average across these. And the theorem says that tau star of xy is always positive, and it's a valid correlation measure here. Tau star of xy is 0 if and only if x is orthogonal to y. X and y are independent. So we can do a practical test to determine whether tau star is 0 or not is through a permutation test. So here is a geometric intuition behind the tau star test. This is similar to the intuition we had for the Kendall tau test. Imagine our 4 samples are like this or like this. In this case, we have a concordant group, and the sign of A of x1 to x4, A of y1 to y4 is going to be positive. On the other hand, if our 4 points are like this, then we have a discordant group. In this case, the sign of A of x1 to x4, A of y1 to y4 is negative. And tau star can be written as 2 times the probability of seeing a concordant group minus the probability of discordant group divided by 3. This statistic is robust to outliers, unlike the distance measure. This is because even if one particular observation is very far, the sign function will prevent its effect on the empirical estimates. Another nice property of this statistic is that we can estimate confidence intervals for our empirical estimate using Hoeffding's inequality. So recall that tau star is 1 over n choose 4 times summation of over I j k l of some function of 4 independent samples. And k of z1 to z4 is sine of A of x1 to x4, A of y1 to y4. So this is the issue here is that this is not a sum of IID samples because z1 to z4 are being reused. So this is a U statistic of order 4 because each element, each term in the summation has 4 independent copies of the random variables. Uh, Note, however, that k is between each term is between -1 and 1. So the range r, which is the length of the interval, is 2. For such a setting, there is a variation of Hoeffding's inequality that can be used for U statistics, and that says that probability, the empirical estimate, minus the true value is greater than epsilon is upper bounded by 2 e to the minus n epsilon square 2e to 2n epsilon square divided by b times r square. So if we have a U statistic of order b, all we change is a b in the denominator. And r is the range here. So in this case, b is 4 because we are using a U statistic of order 4 and r is 2. So probability that tau hat star minus tau star is greater than epsilon is less than 2e to the minus n epsilon square by 8. So now if we do the usual trick, make equal this delta, then we can say that with probability greater than 1 minus delta, tau star lies in tau hat star minus 8 over n log 2 by delta and tau hat star plus 8 over n log 2 by delta. So we can easily compute confidence intervals in this case and then use this to reject the independence hypothesis and so on. So this will be the end of today's lecture. Next week we will continue the discussion of partial correlation graphs and conditional independence graph. So suppose that we have three random variables x, y, and z that satisfy x, z, y, this Markov chain. Then clearly all of them are correlated. So if we were to study a correlation graph, it would look like this. This is z, x, and y. Now x and z are correlated, z and y are correlated, but x and y are also correlated. But if we were to consider partial correlation graph or conditional independence graph, then these graphs would not put an edge between x and y because they are conditionally independent given z. So this is the right structure that we want to use, and next lecture we will see how these methods will allow us to construct such graphs.